Zinc oxide is an inorganic compound with the formula ZnO. ZnO is a white powder that is insoluble in water, and it is widely used as an additive in numerous materials and products including rubbers, plastics, ceramics, glass, cement, lubricants, paints, ointments, adhesives, sealants, pigments, foods, batteries, ferrites, fire retardants, and first aid tapes. It occurs naturally as the mineral zincite, but most zinc oxide is produced synthetically. In materials science, ZnO is a wide-bandgap semiconductor of the 2,6 semiconductor group of the periodic table, and zinc, a transition metal, as a member of the IIB, now 12th, group. The native doping of the semiconductor is N-type. This semiconductor has several favorable properties, including good transparency, high electron mobility, wide bandgap, and strong room temperature luminescence. Those properties are used in emerging applications for transparent electrodes in liquid crystal displays, in energy-saving or heat-protecting windows, and in electronics as thin-film transistors and light-emitting diodes. Chemical properties: ZnO occurs as a white powder. The mineral zincite usually contains manganese and other impurities that confer a yellow to red color. Crystalline zinc oxide is thermochromic, changing from white to yellow when heated and in air reverting to white on cooling. This color change is caused by a small loss of oxygen to the environment at high temperatures to form the non-stoichiometric Zn1 plus XO, where at 800 degrees Celsius, X equals 0.00007. Zinc oxide is an amphoteric oxide. It is nearly insoluble in water, but it is soluble in most acids, such as hydrochloric acid, ZnO plus 2HCl as ZnCl2 plus H2O. Bases also degrade the solid to give soluble zincates, ZnO plus 2NaO plus H2O in Na2, ZnOH, 4. ZnO reacts slowly with fatty acids and oils to produce the corresponding carboxylates, such as oleate or stearate. ZnO forms cement-like products when mixed with a strong aqueous solution of zinc chloride, and these are best described as zinc hydroxychlorides. This cement was used in dentistry. ZnO also forms cement-like material when treated with phosphoric acid. Related materials are used in dentistry. A major component of zinc phosphate cement produced by this reaction is hapite, Zn3, PO4, 2O4 hours 2O. ZnO decomposes into zinc vapor and oxygen at around 1975 degrees Celsius with a standard oxygen pressure. In a carbothermic reaction, heating with carbon converts the oxide into zinc vapor at a much lower temperature. ZnO plus C is Zn, vapor, plus CO. Zinc oxide can react violently with aluminium and magnesium powders, with chlorinated rubber and linseed oil on heating, causing fire and explosion hazard. It reacts with hydrogen sulfide to give the sulfide. This reaction is used commercially. ZnO plus H2S as ZnS plus H2O. Physical properties. Structure: zinc oxide crystallizes in two main forms, hexagonal wurtzite and cubic zinc blende. The wurtzite structure is most stable at ambient conditions and thus most common. The zinc blende form can be stabilized by growing ZnO on substrates with cubic lattice structure. In both cases, the zinc and oxide centers are tetrahedral, the most characteristic geometry for Zn, 2. ZnO converts to the rock salt motif at relatively high pressures, about 10 GPa. Hexagonal and zinc blende polymorphs have no inversion symmetry. This and other lattice symmetry properties result in piezoelectricity of the hexagonal and zinc blende ZnO, and pyroelectricity of hexagonal ZnO. The hexagonal structure has a point group 6M or C6V, and the space group is P63MC or C6V4. The lattice constants are A equals 3.25A and C equals 5.2A. Their ratio Ca to 1.60 is close to the ideal value for hexagonal cell per R equals 1.633. As in most group 2,6 materials, the bonding in ZnO is largely ionic with the corresponding radii of 0.074 nm for Zn2+ and 0.140 nm for O2 a euro. This property accounts for the preferential formation of wurtzite rather than zinc blende structure, as well as the strong piezoelectricity of ZNO. Because of the polar ZNO bonds, zinc and oxygen planes are electrically charged. To maintain electrical neutrality, those planes reconstruct at atomic level in most relative materials, but not in ZNO. Its surfaces are atomically flat, stable and exhibit no reconstruction. This anomaly of ZNO is not fully explained yet. Mechanical properties: ZNO is a relatively soft material with approximate hardness of 4.5 on the Mohs scale. Its elastic constants are smaller than those of relevant 3V semiconductors, such as GaN. The high heat capacity and heat conductivity, low thermal expansion and high melting temperature of ZNO are beneficial for ceramics. ZNO exhibits a very long-lived optical phonon E2, low, with a lifetime as high as 133 picoseconds at 10 K. Among the tetrahedrally bonded semiconductors, it has been stated that ZNO has the highest piezoelectric tensor, or at least one comparable to that of GaN and Al. This property makes it a technologically important material for many piezoelectrical applications, which require a large electromechanical coupling. Electrical properties: ZNO has a relatively large direct band gap of 3.3 eV at room temperature. Advantages associated with a large band gap include higher breakdown voltages, ability to sustain large electric fields, lower electronic noise, and high temperature and high power operation. The band gap of ZNO can further be tuned to 3-4 eV by its alloying with magnesium oxide or cadmium oxide. Most ZNO has N-type character, even in the absence of intentional doping. Non-stoichiometry is typically the origin of N-type character, but the subject remains controversial. An alternative explanation has been proposed, based on theoretical calculations, that unintentional substitutional hydrogen impurities are responsible. Controllable N-type doping is easily achieved by substituting Zn with group III elements such as Al, Ga, In or by substituting oxygen with group VII elements chlorine or iodine. Reliable p-type doping of ZNO remains difficult. This problem originates from low solubility of p-type dopants and their compensation by abundant N-type impurities. This problem is observed with GaN and ZN. Measurement of p-type in intrinsically N-type material is complicated by the inhomogeneity of samples. Current limitations to p-doping does not limit electronic and optoelectronic applications of ZNO, which usually require junctions of N-type and p-type material. Known p-type dopants include group I elements Li, Na, K. Group V elements N, P and Az, as well as copper and silver. However, many of these form deep acceptors and do not produce significant p-type conduction at room temperature. Electron mobility of ZNO strongly varies with temperature and has a maximum of 2000 cm2/s. At 80 K. Data on hole mobility are scarce with values in the range 5-30 cm2/s. Production. For industrial use, ZNO is produced at levels of 105 tons per year by three main processes: indirect process. In the indirect or French process, metallic zinc is melted in a graphite crucible and vaporized at temperatures above 907 °C. Zinc vapor reacts with the oxygen in the air to give ZNO, accompanied by a drop in its temperature and bright luminescence. Zinc oxide particles are transported into a cooling duct and collected in a bag house. This indirect method was popularized by Leclerc in 1844 and therefore is commonly known as the French process. Its product normally consists of agglomerated zinc oxide particles with an average size of 0.1 to a few micrometers. By weight, most of the world's zinc oxide is manufactured via French process. Direct process. The direct or American process starts with diverse contaminated zinc composites, such as zinc ores or smelter byproducts. The zinc precursors are reduced by heating with a source of carbon such as anthracite to produce zinc vapor, which is then oxidized as in the indirect process. Because of the lower purity of the source material, the final product is also of lower quality in the direct process as compared to the indirect one. Wet chemical process. A small amount of industrial production involves wet chemical processes, which start with aqueous solutions of purified zinc salts, from which zinc carbonate or zinc hydroxide is precipitated. The precipitate is then filtered, washed, dried and calcined at temperatures around 800 °C. Laboratory synthesis. A large number of specialized methods exist for producing ZNO for scientific studies and niche applications. These methods can be classified by the resulting ZNO form, temperature, process type and other parameters. Large single crystals can be grown by the gas transport, hydrothermal synthesis, or melt growth. However, because of high vapor pressure of ZNO, growth from the melt is problematic. Growth by gas transport is difficult to control, leaving the hydrothermal method as a preference. Thin films can be produced by chemical vapor deposition, metal-organic vapor phase epitaxy, electrode position, pulsed laser deposition, sputtering, sol-gel synthesis, atomic layer deposition, spray pyrolysis, etc. Ordinary white powdered zinc oxide can be produced in the laboratory by electrolyzing a solution of sodium bicarbonate with a zinc anode. Zinc hydroxide and hydrogen gas are produced. The zinc hydroxide upon heating decomposes to zinc oxide. Zn plus 2 hours 2O is Zn, OH, 2 plus H2, Zn, OH, 2 is ZNO plus H2O, ZNO nanostructures. Nanostructures of ZNO can be synthesized into a variety of morphologies including nanowires, nanorods, tetrapods, nanobelts, nanoflowers, nanoparticles etc. Nanostructures can be obtained with most above-mentioned techniques, at certain conditions, and also with the vapor-liquid-solid method. Rod-like nanostructures of ZNO can be produced via aqueous methods, which are attractive for the following reasons: they are low cost, less hazardous, and thus capable of easy scaling up. The growth occurs at a relatively low temperature, compatible with flexible organic substrates. There is no need for the use of metal catalysts, and thus it can be integrated with well-developed silicon technologies. In addition, there are a variety of parameters that can be tuned to effectively control the morphology and properties of the final product. Wet chemical methods have been demonstrated as a very powerful and versatile technique for growing one-dimensional ZNO nanostructures. The synthesis is typically carried out at temperatures of about 90 °C, in an equimolar aqueous solution of zinc nitrate and hexamine, the latter providing the basic environment. Certain additives, such as polyethylene glycol or polyethylenamine, can improve the aspect ratio of the ZNO nanowires. Doping of the ZNO nanowires has been achieved by adding other metal nitrates to the growth solution. The morphology of the resulting nanostructures can be tuned by changing the parameters relating to the precursor composition or to the thermal treatment. Aligned ZNO nanowires on preceded silicon, glass and gallium nitride substrates have been grown in aqueous solutions using aqueous zinc salts such as zinc nitrate and zinc acetate in basic environments. Preceding substrates with ZNO create sites for homogeneous nucleation of ZNO crystal during the synthesis. Common preceding methods include in situ thermal decomposition of zinc acetate crystallides, spin coating of ZNO nanoparticles and the use of physical vapor deposition methods to deposit ZNO thin films. Preceding can be performed in conjunction with top-down patterning methods such as electron beam lithography and nanosphere lithography to designate nucleation sites prior to growth. Aligned ZNO nanowires can be used in dye-sensitized solar cells and field emission devices. History: zinc compounds were probably used by early humans, in processed and unprocessed forms, as a paint or medicinal ointment, but their composition is uncertain. The use of pushpanjan, probably zinc oxide, as a salve for eyes and open wounds, is mentioned in the Indian medical text the Charaka Samhita, thought to date from 500 BC or before. Zinc oxide ointment is also mentioned by the Greek physician Dioscorides Avicenna mentioned zinc oxide in the Canon of Medicine, which mentioned it as a preferred treatment for a variety of skin conditions, including skin cancer. Though it is no longer used for treating skin cancer, it is still widely used to treat a variety of other skin conditions, in products such as baby powder and creams against diaper rashes, calamine cream, anti-dandruff shampoos, and antiseptic ointments. The Romans produced considerable quantities of brass as early as 200 BC by a cementation process where copper was reacted with zinc oxide. The zinc oxide is thought to have been produced by heating zinc ore in a shaft furnace. This liberated metallic zinc as a vapor, which then ascended the flue and condensed as the oxide. This process was described by dioscorides in the 1st century AD. Zinc oxide has also been recovered from zinc mines at Zora in India, dating from the second half of the 1st millennium BC. This was presumably also made in the same way and used to produce brass. From the 12th to the 16th century zinc and zinc oxide were recognized and produced in India using a primitive form of the direct synthesis process. From India, zinc manufacture moved to China in the 17th century. In 1743, the first European zinc smelter was established in Bristol, United Kingdom. The main usage of zinc oxide was in paints and as an additive to ointments. Zinc white was accepted as a pigment in oil paintings by 1834, but it did not mix well with oil. This problem was quickly solved by optimizing the synthesis of ZNO. In 1845, Leclerc in Paris was producing the oil paint on a large scale, and by 1850, zinc white was being manufactured throughout Europe. The success of zinc white paint was due to its advantages over the traditional white lead. Zinc white is essentially permanent in sunlight, it is not blackened by sulfur-bearing air, it is non-toxic and more economical. Because zinc white is so clean, it is very valuable for making tints with other colors. However, it makes a rather brittle dry film when mixed with other colors. For example, during the late 1890s and early 1900s, some artists used zinc white as a ground for their oil paintings. All those paintings developed cracks over the years. In the recent times, most zinc oxide was used in the rubber industry. In the 1970s, the second largest application of ZNO was photocopying. High-quality ZNO produced by the French process was added into the photocopying paper as a filler. This application was however soon displaced. The applications of zinc oxide powder are numerous, and the principal ones are summarized below. Most applications exploit the reactivity of the oxide as a precursor to other zinc compounds. For material science applications, zinc oxide has high refractive index, high thermal conductivity, binding, antibacterial and UV protection properties. Consequently, it is added into materials and products including plastics, ceramics, glass, cement, rubber, lubricants, paints, ointments, adhesive, sealants, concrete manufacturing, pigments, foods, batteries, ferrites, fire retardants, etc. Rubber manufacture, between 50% and 60% of ZNO uses in the rubber industry. Zinc oxide along with stearic acid is used in the vulcanization of rubber. ZNO additive also protect rubber from fungi and UV light. Ceramic industry consumes a significant amount of zinc oxide, in particular in ceramic glaze and frit compositions. The relatively high heat capacity, thermal conductivity and high temperature stability of ZNO coupled with a comparatively low coefficient of expansion are desirable properties in the production of ceramics. ZNO affects the melting point and optical properties of the glazes, enamels, and ceramic formulations. Zinc oxide is a low expansion. Secondary IOX improves the elasticity of glazes by reducing the change in viscosity as a function of temperature and helps prevent crazing and shivering. By substituting ZNO for BiO and PbO, the heat capacity is decreased and the thermal conductivity is increased. Zinc in small amounts improves the development of glossy and brilliant surfaces. However, in moderate to high amounts, it produces matte and crystalline surfaces. With regard to color, zinc has a complicated nuance. Medicine, zinc oxide is a mixture with about 0.5% iron. 3. Oxide is called calamine and is used in calamine lotion. Two minerals, zincite and hemimorphite, have been historically called calamine. When mixed with eugenol, a ligand, zinc oxide eugenol is formed, which has applications as a restorative and prosthodontic and dentistry. Reflecting the basic properties of ZnO, fine particles of the oxide have deodorizing and antibacterial properties and for that reason are added into materials including cotton fabric, rubber, oral care products, and food packaging. Enhanced antibacterial action of fine particles compared to bulk material is not exclusive to ZnO and is observed for other materials, such as silver. This property is due to the increased surface area of the fine particles. Zinc oxide is widely used to treat a variety of other skin conditions, in products such as baby powder and barrier creams to treat diaper rashes, calamine cream, anti-dandruff shampoos, and antiseptic ointments. It is also a component in tape used by athletes as a bandage to prevent soft tissue damage during workouts. Zinc oxide can be used in ointments, creams, and lotions to protect against sunburn and other damage to the skin caused by ultraviolet light. It is the broadest spectrum UVA and UVB reflector that is approved for use as a sunscreen by the FDA, and is completely photostable. When used as an ingredient in sunscreen, zinc oxide blocks both UVA and UVB rays of ultraviolet light. Zinc oxide and the other most common physical sunscreen, titanium dioxide, are considered to be non-irritating, non-allergenic, and non-comedogenic. Zinc from zinc oxide is, however, slightly absorbed into the skin. Many sunscreens use nanoparticles of zinc oxide because such small particles do not scatter light and therefore do not appear white. There has been concern that they might be absorbed into the skin. A study published in 2010 found a 0.23% to 1.31% of blood zinc levels in venous blood samples could be traced to zinc from ZnO nanoparticles applied to human skin for 5 days, and traces were also found in urine samples. In contrast, a comprehensive review of the medical literature from 2011 says that no evidence of systemic absorption can be found in the literature. Zinc oxide nanoparticles can enhance the antibacterial activity of ciprofloxacin. It has been shown that nano-ZnO, which has the average size between 20 nm and 45 nm, can enhance the antibacterial activity of ciprofloxacin against Staphylococcus aureus and Escherichia coli in vitro. The enhancing effect of this nanomaterial is concentration-dependent against all test strains. This effect may be due to 2 reasons. First, zinc oxide nanoparticles can interfere with NORA protein. NORA is a protein which is developed for conferring resistance in bacteria and has pumping activity that mediate the effluxing of hydrophilic fluoroquinolones from a cell. Second, zinc oxide nanoparticles can interfere with OMF protein. OMF is a membrane protein that is responsible for the permeation of quinolones into the cell. Cigarette filters. Zinc oxide is a constituent of cigarette filters. A filter consisting of charcoal impregnated with zinc oxide and iron oxide removes significant amounts of HCN and H2S from tobacco smoke without affecting its flavor. Food additive. Zinc oxide is added to many food products, including breakfast cereals, as a source of zinc, a necessary nutrient. Some pre-packaged foods also include trace amounts of ZnO even if it is not intended as a nutrient. Zinc oxide was linked to dioxin contamination in pork exports in the 2008 Chilean pork crisis. The contamination was found to be due to dioxin-contaminated zinc oxide used in pig feed. Pigment. Zinc white is used as a pigment in paints and is more opaque than lithopone, but less opaque than titanium dioxide. It is also used in coatings for paper. Chinese white is a special grade of zinc white used in artists' pigments. It is also a main ingredient of mineral makeup. UV absorber, micronized and nanoscale zinc oxide and titanium dioxide provide strong protection against UVA ultraviolet radiation, and are used in suntan lotion, and also in UV-blocking sunglasses for use in space and for protection when welding, following research by scientists at JPL. Coatings. Paints containing zinc oxide powder have long been utilized as anti-corrosive coatings for metals. They are especially effective for galvanized iron. Iron is difficult to protect because its reactivity with organic coatings leads to brittleness and lack of adhesion. Zinc oxide paints retain their flexibility and adherence on such surfaces for many years. ZnO highly N-type doped with Al, Ga, or In is transparent and conductive. ZnO, Al coatings are used for energy-saving or heat-protecting windows. The coating lets the visible part of the spectrum in but either reflects the infrared radiation back into the room or does not let the IR radiation into the room, depending on which side of the window has the coating. Plastics, such as polyethylene naphthalate, can be protected by applying zinc oxide coating. The coating reduces the diffusion of oxygen with pen. Zinc oxide layers can also be used on polycarbonate in outdoor applications. The coating protects PC from solar radiation and decreases the oxidation rate and photoyellowing of PC. Corrosion prevention in nuclear reactors. Zinc oxide depleted in the zinc isotope with the atomic mass 64 is used in corrosion prevention in nuclear pressurized water reactors. The depletion is necessary, because 64Zn is transformed into radioactive 65Zn under irradiation by the reactor neutrons. Methane reforming, zinc oxide is used as a pretreatment step to remove hydrogen sulfide from natural gas following hydrogenation of any sulfur compounds prior to a methane reformer, which can poison the catalyst. At temperatures between about 230°-430 A degrees Celsius, H2S is converted to water by the following reaction: H2S plus ZnO H2O plus ZnS. The zinc sulfide is replaced with fresh zinc oxide when the zinc oxide has been consumed. Potential applications: electronics, ZnO has wide direct band gap. Therefore, its most common potential applications are in laser diodes and light-emitting diodes. Some optoelectronic applications of ZnO overlap with that of Ga-N, which has a similar band gap. Compared to Ga-N, ZnO has a larger exciton binding energy, which results in bright room temperature emission from ZnO. ZnO can be combined with Ga-N for LED applications. For instance, as TCO layer and ZnO nanostructures provide better light-out coupling. Other properties of ZnO favorable for electronic applications include its stability to high-energy radiation and to wet chemical etching. Radiation resistance makes ZnO a suitable candidate for space applications. ZnO is the most promising candidate in the field of random lasers to produce an electronically pumped UV laser source. The pointed tips of ZnO nanorods result in a strong enhancement of an electric field. Therefore, they can be used as field emitters. Aluminium-doped ZnO layers are used as a transparent electrodes. The constituents Zn and Al are much cheaper and less toxic compared to the generally used indium tin oxide. One application which has begun to be commercially available is the use of ZnO as the front contact for solar cells or of liquid crystal displays. Transparent thin-film transistors can be produced with ZnO. As field effect transistors, they even may not need a pi-N junction, thus avoiding the p-type doping problem of ZnO. Some of the field effect transistors even use ZnO nanorods as conducting channels. Zinc oxide nanorod sensor. Zinc oxide nanorod sensors are devices detecting changes in electrical current passing through zinc oxide nanowires due to adsorption of gas molecules. Selectivity to hydrogen gas was achieved by sputtering PD clusters on the nanorod surface. The addition of PD appears to be effective in the catalytic dissociation of hydrogen molecules into atomic hydrogen, increasing the sensitivity of the sensor device. The sensor detects hydrogen concentrations down to 10 parts per million at room temperature, whereas there is no response to oxygen. Spintronics. ZnO has also been considered for spintronics applications. If doped with 1–10% of magnetic ions, ZnO could become ferromagnetic, even at room temperature. Such room temperature ferromagnetism in ZnO, Mn has been observed, but it is not clear yet whether it originates from the matrix itself or from secondary oxide phases. Piezoelectricity. The piezoelectricity in textile fibers coated in ZnO have been shown capable of fabricating self-powered nanosystems with everyday mechanical stress from wind or body movements. In 2008, the Center for Nanostructure Characterization at the Georgia Institute of Technology reported producing an electricity-generating device delivering alternating current by stretching and releasing zinc oxide nanowires. This mini-generator creates an oscillating voltage up to 45 millivolts, converting close to 7% of the applied mechanical energy into electricity. Researchers used wires with lengths of 0.2 to 0.3 ohm and diameters of 3 to 5 micrometers, but the device could be scaled down to smaller size. Safety. As a food additive, zinc oxide is on the US FDA's list of generally recognized as safe, or GRA, substances. Zinc oxide itself is non-toxic. However, it is hazardous to inhale zinc oxide fumes, as generated when zinc or zinc alloys are melted and oxidized at high temperature. This problem occurs while melting brass because the melting point of brass is close to the boiling point of zinc. Exposure to zinc oxide in the air, which also occurs while welding galvanized steel, can result in a nervous malady called metal fume fever. For this reason, typically galvanized steel is not welded, or the zinc is removed first. See also. References. Reviews Oscar al. A comprehensive review of ZNO materials and devices JAPPL. Viz 98041301 doi, 10.1063/1.1992666, A. Barkeen and A. Warg ZNO epitaxial growth chapter in a OE comprehensive semiconductor science and technology A 6-volume encyclopedia, Elsevier, edited by Palab Bhattacharya, Roberto Forneri and Hiroshi Kamimura, ISBN 978-0-444-53143-8, S. Baruo and J. Dutta hydrothermal growth of ZNO nanostructures Sci. Technol. ADV. Mater. 10.01.3001 doi, 10.108810013001, Arjanish al. Transition metal dope TO2 and ZNO present status of the field J. Phys Condens. Matter 17 R657 doi, 10.108817R01, YW Heo al. ZNO nanowire growth and devices Mater. Sci. Eng. R47 doi, 10.1016/JMSER. 2004.09.001, Kling-Schoen ZNO, From Basics Towards Applications Phys. Stat. Salidi 244-3027 doi, 10.1002/PSSB 200,743,072, Kling-Schoen ZNO, Material, Physics and Applications ChemFilm 8782 doi, 10.1002/CPHC 200,700,002, J. G. Louis al. Quasi-one-dimensional metal oxide materials Eurosynthesis, Properties and Applications Mater. Sci. Eng. R5249 doi, 10.1016/JMSER. 2006.04.002, SU and ZL Wang One-Dimensional ZNO Nanostructures, Solution Growth and Functional Properties NanoRes 41013 doi, 10.1007 per second 12274-011-0160-7, SU and ZL Wang Oxide Nanowire Arrays for Light-Emitting Diodes and Piezoelectric Energy Harvesters Pure APPL. Chem 832171 doi, 10.1351/PACCON 11-08-17, External Links, Zincite Properties, International Chemical Safety Card 0208. NIOSH Pocket Guide to Chemical Hazards. Pesticide Properties Database Record for Zinc Oxide.